This 2019 paper 2 question 7, so it's a geometry question and we have to figure out what AD is here. So it might not be super clear what to do, but I think the thing that you should try first is maybe look at this triangle, just because the triangle is there. We don't really have this side here, so it wouldn't make sense to look at the bottom triangle. So let's just look at that top triangle first. So if we have A and we have D and we have O, well then we know this side is 90. This side here is a bit trickier, but we know that O to B is 90 because they tell us that it's a radius, and we know that this part from D to B is 30. So that means from O to D must be 60, because then 60 plus 30 will give us 90. So this side must be 60, and then this is a right angle. And the reason this is a right angle is because we know that ODC here is a right angle. They tell us that. Well, they actually say that OB is perpendicular to AC, which means that this is also a right angle. So then we just can figure out what AD is quite easily. I'll just call it X, and because we have a right angle triangle, we can use Pythagoras' theorem. So X squared plus 60 squared should give us 90 squared, which means that X squared should be equal to 90 squared minus 60 squared. So that means that X will just be equal to the square root of 90 squared minus 60 squared. And you can just put that into your calculator, and what you should end up getting is 30 root 5 centimeters. Don't forget the unit. And that's in the way that they wanted. They wanted a number times the square root of a number, and they're whole numbers, they're integers, and that's exactly what we have. Then we have to find the angle DOA in radians. So it should be easy enough, because you can see in this triangle, DOA is just here. So we might use cos, because we have the adjacent to the hypotenuse. We could use this, but it has square roots, a bit messy. So what we can say is that cos of that angle, and I might just call it A. So cos of the angle A will be equal to 60 divided by 90. So then you can just do cos inverse on both sides. So A will be equal to the cos inverse of 60 over 90. And you can just put that into your calculator. Make sure it's in radians mode. And to 2 decimal places, you should get 0.84 radians as your answer. Then we have to find the area of the segment ABC. So that's this little bit right here. So the way that we can do it is we can find the area of this sector here. And then we can subtract off the area of this triangle up here. So the way that we get the area of a sector, there is a formula in the tables book, but I'm going to show where it comes from really quickly because it's not too difficult. So the entire circle is pi r squared, but we don't want the whole thing. We want to think about the entire circle has 2 pi radians, but we don't want the entire 2 pi radians. We want theta out of the 2 pi radians. So if theta was equal to 2 pi, we'd have 2 pi over 2 pi, which is 1, so that's the whole circle. If theta was half of 2 pi, which is basically half of the circle, we'd end up having a half here, so we get half of the area. So how many angles do we have? Well, we know that the angle DOA is 0.84 radians, so that's the angle just here. So if we want the entire angle, that's going to be double 0.84. So that's what our angle is going to be. So the area will be pi times the radius squared. Let's just put it in meters because we do want our answer in meters squared. So instead of writing 90 centimeters for the radius, I'm going to write 0.9 meters squared multiplied by, and the angle will be 2 multiplied by 0.84 out of the 2 pi radians. And we can just check what that is. You can just put it into your calculator. And what you should end up getting is roughly 0.6804 meters squared. And I'm just going to leave 4 decimal places for now. We'll do 2 at the end. We're just kind of want to maintain accuracy for now. So now what we want to do is we want to find out what is the area of the triangle. So the area of the triangle, so for the triangle, the area will be equal to half the base times the perpendicular height. So we'll have a half. The base here, so remember that A to D, that was 30 root 5, and then because it's symmetrical, the entire thing will be 60 root 5, so we're just multiplying that by 2, so we'll have 60 root 5, because that's 30 root 5 times 2, and then the height is going to be, well, remember that O to B was 90, this part is 30, so O to D was 60, so that's the height of the triangle. So that'll be 60, and just this is in centimeters, so we will have to convert it to meters, because this is in centimeters. Each of these is in centimeters, so you have centimeters and centimeters. Multiply those together and we'll end up getting centimeters squared, but we can check what we get. And we end up getting 1,800 root 5 centimeters squared. To put that into meters, what we want to do is we want to say it's 1,800 root 5. And instead of saying 1 centimeter squared, we can write that as 0.01 meters, the whole thing squared. So what that means for us is when we're doing this, we're going to multiply it by 0.01 squared, and then we have meters squared because we're squaring each of these things because they're multiplied together. And this ends up giving you 9 root 5 over 50, and that's going to be in meters squared. So then to get the area of the segment, we're going to take the area of the sector minus this area. So area of the segment will be equal to, it'll be 0.6804 meters squared minus 9 root 5 over 50 meters squared. And when you put that into your calculator, what you should end up getting is 0.28 meters squared, and that's correct to 2 decimal places. The way to find the volume of the trough, so the way that works is we're basically going to multiply this area, and we're going to stretch it out by 2.5 meters, so that's why we're multiplying. So the volume will just be equal to the cross-sectional area, which is 0.28 meters squared, and then we're going to stretch that out by 2.5 meters. Again, that's just this length, and then they'll give us an answer in meters cubed, so that's all good, and you can just check what that is, and you end up getting 0.7 meters cubed as your answer. Then we're given a shape here, and we have to find the volume of the upper half. So the top shape is a hemisphere, so the volume of that is going to end up just being, so the volume of a full sphere is 4/3 pi r cubed. So in this case, we're just going to have half of that, which will be 2/3 pi, and you can see the radius is 1.25 in centimeters, and I'll have that cubed, plus and then we have the cylinder here. So it does say that's hemisphere, a cylinder, and a cone. So this cylinder, the height, so it's going to be pi r squared h. So we're going to have pi. The radius, it says for all of them, the radius is 1.25. So we'll have 1.25 squared times the height, which is going to be 3.5, plus, and then we have the cone down here. The cone has a height of 1.5. So to get the volume of the cone, we'll have 1/3 pi. The radius is the same, 1.25. We're going to square that, then multiply by the height, which is 1.5, and you can just put that into your calculator, and you end up getting, at 2 decimal places, you should get 23.73 centimeters cubed. Then the sand starts flowing down, and at a certain time, 98% is in the bottom half. We need to find the height of the remaining sand, so h on this diagram. So that means that 2%, this is 2% of the volume left here. So let's get 2%, 0.02, multiplied by our original volume, which is 23.73. And that'll tell us how the volume of this shaded cone that we need to find. And it ends up being 4746 centimeters cubed as our volume. Cool. So what we could do now is we could say that the volume is equal to this 0.4746 centimeters cubed, and that'll just be equal to the volume of a cone, which is 1/3 pi r squared h. So 1/3 pi r squared h. However, we have 2 unknowns here, so there's not really much we can do. So what we need to figure out a relationship between r and h to get rid of one of these unknowns. So the way that we can think about this is, hopefully you've done some similar questions before, but because this is a cone within a cone, we already know something about the relationship between r and h, because we know the relationship between r and h for the big cone. So you can do this out, but they actually end up being similar triangles. So if I just draw out, I'm going to make colors on them here. So we have a red triangle here, and then we have a green triangle here, right? And you can see that they're just scaled up versions of each other, so they are similar triangles. So if I just show you why. So if we have, this is the big triangle, and this is the small triangle. So first of all, they both have this right angle, and that's just because they are right cones. I'm not sure if it says that, but cones are always at right angles. The height and the base are at right angles. They both have this angle in common down here at the bottom. So this angle down here, that's an angle in the big triangle and the small triangle. So this angle is the same in both of them. And if 2 angles are the same, that means all 3 angles are the same. Because we know that all 3 angles should add up to 180. So if these 2 are the same, this one also must be the same in order to make sure that they both add up to 180. So these are similar triangles, and for these kind of questions, they don't ask you to prove that formally. They just want you to notice that they're similar triangles and use that fact. But if it was a geometry question, you'd have to say why all the angles are equal. So then for this big triangle, the radius here is 1.25, and the height is 1.5. And then for the small triangle, the radius is r and the height is h. Because these are similar triangles, their sides are going to be in ratios to each other. You can also use tan, and it's going to be tan of the same angle, so the ratio of the opposite and the adjacent is going to be the same. That's just another way of thinking about it, but you'd probably think about the similar triangles way. It just makes a little more sense. So we'd have 1.25, which is the top side here, divided by r, would be equal to 1.5 divided by h. So we might just replace h in this equation because it's going to be easier. We don't have to square it or anything. So if we bring the h up, we get h equals, bring the r up to this side, we'll have 1.5r, and divide down the 1.25, and we get divided by 1.25. So now if we take this equation, we can rewrite 0.4746 centimeters cubed will be equal to a third pi r squared, and instead of h, we can write that as 1.5 r over 1.25. So then, to get the r's by themselves, we can multiply the 3 up to the left-hand side. So I'm going to keep the left-hand side here. We're going to multiply it by 3. So let's bring the 3 up. We can divide it by pi, divide the pi down. And then we can multiply the 1.25 up. So we can multiply this by 1.25. And then we can divide the 1.5 down. So divide down the 1.5, so it's 1.5 times pi. And then on the right-hand side, we've gotten rid of all the numbers, so we just have r cubed. So to get r, we can just do the cube root, or the power of a third on both sides. I think it's nicer to think about it as the power of a third. It's probably easier to type into the calculator too, because then 3 times a third gives us 1, so that just gives us r on the right-hand side. And then on the left-hand side, we're just going to have all this stuff to the power of a third. So you can just put that into your calculator, and you end up getting I'll just give 4 decimal places for now, 7228. And the reason I'm giving 4 is because this isn't our final answer. We need to figure out what the height is. So it's quite easy. The height is just going to be 1.5 times r divided by 1.25. So I'll have 1.5 times 0.7228 over 1.25. And you can figure out what that is. And it ends up being, to 2 decimal places, 0.87. And the unit's going to be in centimeters because everything else was in centimeters. So yeah, there we go.